All right. Hello, everybody. I wanted to take this as an opportunity to talk to you about the experiment that you're going to be doing this upcoming week. This experiment is one that's really it's got a couple of different angles to it. One of those angles is getting familiar with your lab surroundings. Also, kind of not really changing the language that you use, but um, thinking about something that you did in Chem 2, but applying it to a biochemistry lab. And that thing that you did in Chem 2 was preparing buffers. Generally, when you prepared a buffer, you probably were given like a target pH, and then asked to basically use a weak acid and a strong base and prepare a buffer at that specified pH. Well, that's not so radically different at all from what we do in biochemistry. What what probably makes this a little bit different, however, is the substances that we're using to prepare that buffer. In addition to that, in a Chem 2 setting, it's entirely possible that you'll be told prepare a buffer with a pH of 10.5 or 5.6, 3.5, something that's outside of a neutral range. Whereas in a biochemistry lab, it's pretty common, or I would say that it's most common that um, the pH for the buffer that you're going to prepare is going to have a pH within a range of approximately 7.2 to 7.4, because that's the range that most organisms live within. Um, there are, however, as I mentioned in this introduction, there are some outliers. For instance, if you're studying a lysosomal protein, well, the pH within that membrane-bound organelle is approximately 4.5 to 5. So in that case, you would use a different buffering solution than you would for a cytosolic pH. Um, so what I really want you to do with this is learn about some different components of a buffer. So some of those different components, I'll get into those different components in just a moment. But whenever you are, sorry about that. So whenever you're preparing a buffer, your components are a weak acid and a strong base, and therefore what you're basically putting in balance with one another is the acid form of something and the conjugate base. So as I kind of go through this, one of the first things that we look at is the Henderson-Hasselbalch equation, which I have the typo myself. It's actually the Henderson-Hasselbalch, Hasselbalch, named for Carl Albert, not Albert, Carl Albert Hasselbalch, a Danish physician and chemist, along with Henderson. And Henderson, that was Lawrence Joseph Henderson. So anyway, so the Henderson-Hasselbalch equation is pH equals pKa plus the log of the concentrated form of the concentrated conjugate base divided by the concentration of the weak acid. So we look at the ratio of our conjugate base to our acid. Now, if you look at something like acetic acid, for instance, well, then your acetate ion displayed here is the deprotonated form, or is the conjugate, or is our base, and CH3COOH is our acid. So we look at a ratio of those two to one another, and we look at the pKa, and we can prepare a buffer based on that. Now, a good rule of thumb is that any molecule is going to have a buffering range plus or minus 1 of its pH. For instance, acetic acid has a pKa of approximately 4.75. You might see it reported as 4.8. Well, plus or minus 1 from that means that you're going to have a buffering range that goes as high as as high as 5.75 and as low as 3.75. So an acetic acid or an acetate buffer, or a sodium acetate buffer, is something that will work at a pH of, or it's going to be able to be functional at a pH of 4.5, 5.5. 6.5, on the other hand, that's outside of the buffering range. So any minor addition of an acid or a base is going to cause that pH to go up or is going to cause that pH of that solution to change pretty drastically. So buffering range, plus or minus 1 of the pKa. Now, acetic acid is an example of an acid that has 1 pKa value. Well, many times in a biological setting, we're using molecules that have multiple pKa's. For instance, phosphate buffers. Well, phosphate buffers have 3 pKa's because if you think about phosphoric acid, it's H3PO4. Has a total of 3 pKa's, 2.14, 7.20, and 12.37. So what that means is that this molecule has 3 buffering ranges. Now, whenever it comes to kind of the list of buffers for a biochemistry lab or in a biological system, there's a list of buffers known as goods buffers. And these are named after, I think it's Norman Good. I can't remember his exact first name. But, oh, here it is. Yeah, Norman E. Good. He cataloged a list of buffers that meet a certain criteria. So he reported this, or he submitted this as a paper in 1966. Hydrogen ion buffers for biological research. He just came up with a list of buffers that were good and came up with a criteria for those buffers. For instance, there were a total of 10 different criteria that were used to select these buffering agents. First of all, they all have a pKa between 6 and 8. Second, they're all easily prepared buffers. Third, they are all highly soluble. Fourth, they will not absorb light of wavelengths greater than 230 nanometers. And finally, they will not influence any biochemical reaction. So this list of buffers that Good came up with has kind of been almost the I guess you could say the gold standard of buffers that are used in biological settings. Now, to name a few of the original buffers, heaps, MES, and pipes are all buffers that are very effective for biochemistry and molecular biology because they all meet those criteria. Now, one thing that I like to bring up that's a little bit foreshadowing is I guess it would be the third item here. The third criteria for goods buffers is that they did not absorb light of greater than 230 nanometers. It's important to note that 230 nanometer line, or that 230 nanometer wavelength, because when you get to something like 260 nanometers or 280 nanometers, absorbing light within that range, well, if you're dealing with a protein or nucleic acid, then if your sample absorbs light, or if the buffer that your sample is prepared in absorbs light at 260 or 280 nanometers, well, that's going to really impede your ability to study DNA or protein because of the fact that both of those absorb light at DNA and protein absorb light within the 260 and 280 nanometer range. If your buffer absorbs light within that same range, you can't really conclusively say anything about the sample that you're wanting to analyze. You can't say anything about the amount of protein that's there because that buffer has also absorbed light within that range. So it basically is the buffer itself, non-goods buffers would basically appear as a contaminant almost. Okay, so next up, so a couple of things with respect to buffers. An acid and the conjugate base, plus or minus 1 of the pKa is a buffering range. Goods buffers is a list of buffers that are very effective for molecular biology and biochemical work. Now, next up, buffer additives. So it's pretty common if you prepare a buffer, you're going to add something else to it. And those different substances contribute a lot to either the sample that you're analyzing or perhaps the stability of a protein or something within your sample. So it's very common to add different substances buffers. For example, salts, detergents, sugars, metal ions, metal chelators, protease inhibitors, ligands, and reducing agents. Now, all of these different things have different purposes. For instance, metal ions and metal chelators. Well, a metal chelator is basically a molecule that's going to grab onto a metal and kind of like suck it out of solution. Metal ions, on the other hand, that would be the opposite of a metal chelator. So whenever you're preparing a buffer, it's very important, if you've been given a recipe for a buffer, it's important to know what you're adding and why you're adding. Salts, I would argue, are probably the most common things to add to buffers. Sodium chloride, potassium chloride, they're very easily going to dissociate, going to be stable in solution. They'll provide a strong cation and a strong anion. The presence of these two ions can help to, I apologize, they can help to keep a protein stable. Now, protein stable and soluble. Now, although that protein solubility can be a reason for adding salt, something like sodium chloride can be added to a buffer for downstream purposes. For instance, if you are trying to purify a protein or elute a protein. If you remember back to our protein purification worksheet, we used an elution buffer. So whenever you're doing the ion exchange chromatography, we used an elution buffer. That elution buffer had something like sodium chloride in it, or you changed the pH. And the intent of that was to get your protein that was adhering to that, say, ion exchange chromatography column to see a cation come through and bind to that cation and release from the column. Okay, so salts are regularly added. Detergents. Well, detergents are also added to buffers on a regular basis. Now, when you think about a detergent is a long alkyl chain. They are, in most buffers, the role that they're playing is they're going to help solubilize a protein. They're going to help disrupt the biological membrane, disrupt membrane components. They're going to do a number of different things. They're largely going to have to do with like protein solubility or disrupting a membrane or something like that. Metal ions and metal chelators are generally not going to be added to the same buffer because, like I said previously, a metal chelator binds to a metal cation and kind of removes it from the solution. Well, if you're adding a chelator to a solution and then adding a metal cation, you're basically adding this metal ion that you try to chelate and remove from the solution. So kind of is backwards there. Examples of, or it's kind of, you're causing a problem for yourself. Add the chelator to remove metal ions, but then why would you add metal ions if you just tried to remove those metal ions? Okay. So common chelators that are added are EDTA and EGTA. EDTA binds magnesium cations, Mg2+, whereas EGTA very tightly binds calcium ions. And these are one of the other things that they're going to do is they will inhibit the activity of nucleases and other metal activated enzymes. So if you're trying to work with a DNA binding protein, you probably don't want nucleases to be very active because then that's going to chomp up any of the DNA that's present in your solution. So EDTA and EGTA, they're going to do the same thing, but they're going to act on different metals. Then after you think about the different additives, it's important to think about how to prepare a buffer. Now, is simply put, putting or preparing a buffer is, oh, well, you add this solid, then you add water, and then boom, it's done. You might have to put it on a stir plate or something like that, but largely it's done. Well, it's still important to consider a couple of things. For example, in many cases, you're going to work with something, or what's known as a hydrated salt, something like BaCl2 to H2O. Okay, so that's barium chloride dihydrate. Now, that barium chloride dihydrate, if you're going to prepare that barium chloride dihydrate solution, well, a very good question to ask is, do I need to account for the mass of water? And the answer is absolutely you do. So what I've shown, what I showed below is a calculation for what mass of barium chloride do you need if you're making a 0.15 molar solution of barium chloride, and specifically making 1 liter of a 0.15 molar solution. So below you'll see the difference in the dimensional analysis required for making a 0.15 molar solution when you're using an anhydrous barium chloride. So that's the solid where it's just BaCl2. You have 0.15 moles BaCl2 in 1 liter. Well, 1 mole of BaCl2 has a mass of 207.33. Multiply 0.15 by 207.33, and you get that if you wanted to make a 0.15 molar or 1 liter of a 0.15 molar barium chloride solution, you would need 31.0955 grams of barium chloride. Now, if we compare that to this hydrated salt, this barium chloride dihydrate, barium chloride dihydrate has a molecular mass of 243.33. Okay, the difference between those two substances is, well, the mass of 2 moles of water. Okay, so if you wanted to do the exact same concentration of this barium chloride, you would have to account for that mass differential. So you want 0.150 moles of BaCl2. Well, you have to do the dimensional analysis to consider the substance that you're working with. 1 mole of BaCl2 is present in 1 mole of BaCl2 dihydrate. Divide that by 1 mole BaCl2 DH2O, multiply across the top by 243.33. So 0.15 times 1 times 243.33 divided by 1 times 1 times 1 gives you 36.4995 grams of BaCl2. So you do have to take into consideration the mass of that dihydrate when you're doing this sort of calculation. Now, what this is all leading to is using a couple of different things. One thing is we're going to be using the LabQuest 2 pH meters whenever we're preparing our buffers. So you have to calibrate your pH meter. We're going to have buffer solutions of 4, 7, and 10. The solutions that we'll need to use today or use in lab are 7 and 10. Now here's the directions for how to calibrate your pH meter. Okay. Once you've done that, go through that process. Once you've done that, I want you to go ahead and walk around the lab and take a look at some of the buffers and some of the solutions that we have, the substances that we have in lab. You can start out by, Google goods buffers. It's a good place to start because you have that list. You can then compare that to what is available in the lab. In addition to that, you can find sodium acetate, sodium phosphate. I want you to come up with a name, draw the chemical, or what's the chemical name and the structure of that, and what pKa's does it have. As a result, based on the pKa's that are present for that molecule, what pH range will this work within? And then finally, is this in stock? And well, if you found it in the lab, yes, absolutely, it's in stock. So I want you to find a total of 3, 4, 5, 6, 7 different substances in our lab that you can use as a buffer. Now, what I want you to do, and this is described in the later pages, is I want you to prepare a buffer or prepare 2 different buffers. One with a pH of about 7.5 and one with a pH of 10.0. So what that means is if you look at that list of goods buffers, that's a good place to look because then you can say what the pKa's of them are. And then based on those pKa's, you can say, oh, this would be a perfect buffer for a pH of 10. This would be a perfect buffer for a pH of 7.5. I think that's ultimately going to be very helpful in order, or as you complete your lab. But there's a couple more pages to work through, a little bit more math to work through, some more calculations. And then one thing that I think is important is I want you to look at that molecule and identify the protonated form of the molecule and the deprotonated form of your molecule. Then do the same thing at a pH of 10, because what we are concerned with is that ratio, that balance between the the protonated and deprotonated form. So this is page 9, describes basically how to prepare that pH of 7.5 buffer, and then page 10 tells you how to prepare that pH of 10 buffer. This one's going to be 150 millimolar, whereas the pH of 7.5 is going to be a 50 millimolar buffer. So you need to work through figuring out the amount of that substance that you need. Now, I'll ask you to, you can do this independently. Look at these independently outside of lab. Look up these different additives and figure out what kind of additive it is. EDTA, EGTA. Spoiler alert, those are both chelators. Azide, you might also find that as sodium azide. SDS, also known as sodium dodecyl sulfate. Urea, DTT, also known as dithiothriotol. Triton X100, tween 20. BSA, also known as bovine serum albumin. Glycerol, and sucrose. I want you to look up all those different additives and see what they are. Then I want you to come up with and answer some questions about different types of buffers. What's a lysis buffer? What's an elution buffer? What's a wash buffer? Now, those are kind of commonly used terms in a biochemistry lab. I want you to find out a definition for them. And this doesn't have to be a formal Webster's or style definition, but something that describes what it is. I guess that's a definition. Then as I just go through these last few questions, I just want to make sure that I think there's one question. This question right here, if the calculated masses in the above question were combined into one 200 ml solution, what would the final concentration of phosphate be? Don't worry about answering that question. But then last thing before you leave, I want you to make sure that you label your work. Put your partner's initials, your initials, describe the buffer, and then put the date. Okay, everybody. I believe that's it. So I hope this is helpful. I hope you have a little bit more insight into what is the concept approach to preparing a buffer, and I hope that you kind of jogged your memory on some of those calculations with the Henderson-Hasselbalch equation. Other than that, though, have a good day.